At the recent CVPR 2023 conference, Ashok Elluswamy gave a very interesting talk. In a lot of ways, it was repeating information that we already knew, but the new thing he revealed will likely change full self-driving in a substantial way and could actually change robotics in general. Let's take a look. Hey y'all, it's Dr. Know-It-All. So this is part 2 of a 3 or 4 part series. I'll link the last one up here. It's the last video that I did. The next one in the series is going to be about stop signs, and then I'm going to come back to another CVPR talk from Phil Dwan in a couple of days. These ones take forever to create. So I'm going to sort of do a little bit easier one in between just to give myself a little more time. The second thing I want to mention really quickly, you'll see here that the resolution is pretty terrible on the video. This is something that was recorded by one of the conference attendees, almost definitely. It's not official CVPR, but it's been up for about 8 or 9 days at this point, and nobody has asked it to be taken down at this point. So I'm like, okay, I'm going to use it. And again, I will link the original in the description, of course, and I'm going to just do a couple of video clips. They are a little bit on the long side, but the entire thing is about 32 minutes long. So I highly recommend watching the whole thing for the context around this, but I did want to lay that out. I think that CVPR will officially release these videos in August sometime based on last year, but given the fact that this is out there and it hasn't been taken down, I'll go for it for now. If they tell me to take it down, I will repost the video in August once the official CVPR thing comes out with the better quality video. All right, so like I said in the introduction, a lot of this stuff is recapped. I'm going to kind of blast through a lot of that. I have a whole playlist of AI Day 2, and I'll put the playlist up there so you can check that out at your heart's content. It goes into occupancy networks, goes into most of the stuff that we're going to talk about here, but it is useful to recap this and see a few new things, especially statistics right now, right? So as Ashok says, there are 400,000 vehicles in the US and Canada are actively using full self-driving beta right now. They are up to 250 million miles to date. I believe the last metric that we saw was 100 million miles. So they're, the exponential expansion is happening. We're getting a lot more miles driven with full self-driving beta these days. And of course, no radar, LiDAR, ultrasonics, HD maps, etc., etc. The really interesting thing was Ashok at one point said, you can go out and buy a car and drive this today. And I was like, wow, that is really wild, because most of the time when you go to conferences like this, almost all of the stuff is like lab research kind of things, right? It's like, we did this thing and it's really cool, but nobody has access to it unless they have giant GPU clusters and things like that to do the research with them. But the fact that us just normal run-of-the-mill people can go out and actually drive a research project is pretty darn cool. The next thing he touches on, of course, is occupancy networks. That's a recap, again, from AI Day 2022, and I believe CVPR last year as well. But this is something that's only been around for about a year. My understanding when Ashok talked about it was that this was kind of a weekend project that he just sort of took on himself and just made it happen, and then it turned out to be really, really useful. The basic idea of an occupancy network is it's putting geometry before ontology. In other words, it just says, is this voxel of space, this three-dimensional pixel of space, occupied or is it not? And then figure out all the rest of it later. And basically the car just needs to know, even if it doesn't know exactly what something is, it needs to know whether that part of space is occupied or not. And if it is, then it needs to avoid that at all costs. And then it can start doing semantics and ontology and things. And you can see in this still frame capture that we've got things like parked cars and stuff like that that are kind of an orange color. I think that the curbs are green and then background stuff is white. So there's a basic ontology that's being put on top of this. And then of course it can pass that down to another neural network that can get into more detail about, is that a pedestrian or something? And if it is, what are the kinematics of that? So this is kind of you could call it dumb, but it's actually really important first step that happens. And then things get more and more refined over time. And also it's really important to note that this occupancy network is persistent through time and through occlusions. In other words, it's not just a single frame or a single 360-degree view that's been projected out into 3D. It's a moving version of that. And over time, it can see what things are moving through space along with you. And that's crucially important. It's very, very important to know what's moving through space with you and what's static in the world, and to define what the ground is, what is the drivable space. All of that kind of stuff is really, really complicated. And the occupancy network has been a major, major breakthrough in terms of how the car can drive through a very complicated world. And of course, as Ashok says, it is robust to ontology and semantics errors. In other words, it doesn't have to be able to label everything to know if that space is occupied, with some caveats that we're going to talk about later on in this video. And very importantly, it's not just usable in cars, but also in TeslaBot, in Optimus, the Tesla bot. And we saw that at AI Day 2022. We saw that there was an occupancy network that had been versioned out for TeslaBot as well. Interestingly enough, and we'll get back to this in a question and answer part that Ashok did at the end of his, but also in Phil's talk as well, he talked about resolution where it matters in terms of the occupancy network. So sort of table that idea for a little bit, but it is going to be very, very important. And as he says, this is very similar to NeRFs or neural radiance fields, but it runs in real time rather than having to be post-processed later on. And of course, it lacks a lot of the fine-grained details, texturing, all of that kind of stuff that comes along with NeRFs, but it runs way, way faster than NeRFs. NeRFs are rather slow, but we're going to get back to NeRFs and a hybrid version of NeRFs later on in this talk as well. In the next slide, Ashok says that the architecture is very straightforward. I find that a little bit, kind of a laugh out loud sort of thing. It's, for them, I guess it's straightforward. But basically, you take the images, you process the images, you do spatial and temporal alignment, you do occupancy network, and then very importantly, from the latent space, which is a compressed space of information, you will then use deconvolution to deconvolve this back into the three-dimensional space that it's projecting onto. And that's where the variable voxel size can actually be tweaked. And that's a really important aspect of this network. Actually, he kind of mentioned it in passing, but it's hugely important that you can change the output deconvolutions and therefore change the sort of resolution of your output. Obviously, with the consequence of smaller and smaller voxels mean more of them to fill the space, which means more compute time, which means, when you're running it on a car with a mobile processor, basically, there's some trade-offs in terms of doing finer resolution versus compute time. And then we move on to what John Emmons did a talk about at AI Day 2022 last year, which is generative modeling of lanes using a ChatGPT sort of large language model tokenized version of creating this. Now, Ashok goes into more detail about this. I'll put the original up here if you're interested in having a look at it. But basically, he says that some of the issues are that roads just go on forever. As opposed to a car which has a finite volume in space, roads basically go as far as you can see. They separate, they fork, they merge. So they're kind of more of a graph structure instead of like language, which is just linear, right? One word comes after another. Here you've got branching and you've got debranching and you've got all sorts of crazy things. And there's a great deal of uncertainty. Things can become occluded. There can be an argument about, is that one lane or two lanes? There's a lot of different stuff going on. But basically what they've done is they've tokenized roads into like language, right? The cat sat in the hat. They've just tokenized it into different things like straight lane, turning lane, right turning lane, left turning lane, fork lane, merge lane, things like that. So they've got these tokens and they're building out a graph in real time of what's happening, particularly at intersections where it gets really, really complicated. And then the car is able to move through those intersections, those complicated situations, because it's sort of following the grammar of a language. You could think about it that way. It's very, very cool how this works. Really interesting solution to a very, very difficult problem. In fact, as you see in the slide, he says overall it's quite obnoxious to predict. And what they have to do is create a bunch of sort of tokenized polylines and things like that to create that. But anyway, it's surprisingly difficult. It's something that human beings don't have that much of a problem with because of the nature of the way that we interact with the world. But this is a very, very complicated thing, and it's a really elegant solution that they've come up with. Doesn't work perfectly yet, obviously, but it's a really elegant solution. And one really cool aspect of this is that they don't need to do any post-processing. He says little to no post-processing of the output. I think it runs in about 10 milliseconds, so it's able to run this quickly. That actually might be a mistake. There might be something else that runs in 10 milliseconds. But anyway, it runs very, very fast, and it doesn't need post-processing. So the output of it can be used directly by the downstream neural networks, which is really important because it's providing clean data, because it's basically abstracting out the reality of things into a language model. And then real quickly getting into more ontology and semantics, you have object prediction and properties. In other words, it knows that that looks like a person. They could be crossing the street. They have approximately these kinematics, in terms of being able to move quickly, sideways, forward, backward. A car is a car. It has a certain kinematics as well, certain motion capabilities. All of that kind of stuff is obviously crucially important, but it's been gone over before, so I'm going to move through this quickly as well. And very importantly, Ashok talks about how these models are multimodal. In other words, they don't just take in video, but they also take in the internal measurement unit, the IMU, that's inside the car, which is basically your inner ear. It's the thing that tells you the acceleration, the jerk, the yaw, all of that kind of stuff is very important. And they utilize that to make the car drive as smoothly as possible, because it's one thing if the car can get through a scene and can do well, or scene reality, if it can do well in terms of being safe and not running into things. But if it's constantly going like like jerking and back and forth and all of that, the human driver will be incredibly uncomfortable and will turn it off because they won't want to use something like that. So smoothness is important, and the multimodality of the inputs to the system is also crucially important for it to understand how to drive smoothly in these situations. And one thing he mentioned briefly, but didn't really go through in great detail, but it has become a problem with the latest versions of the builds, is the multimodality of using low resolution map data. In other words, Google Maps is feeding it sometimes incorrect information as an input, and therefore the car is not driving properly in some certain situations. Someone analyzed one of Chuck Cook's problem areas where the car was going into a suicide lane and then pulling back out again, and realized that it's actually Maps data telling the vehicle to go there and then move back out again. So there is clearly issues with that modality of the low resolution maps and the navigation information. So that is something that Tesla is going to have to look into. My prediction is that eventually they're going to move away from using anybody else's map solution and use their own, but we will see, time will tell. And then I wanted to point out this picture again, super low resolution. But if you look here, you can see all of these path predictions that it's doing: 2 right-hand lane turns, 3 left-hand lane turns, and a straight lane, going through straight. This is something I don't believe that you can see in the normal version of full self-driving beta, but clearly they've got this advanced version where you can visualize more things, but you can see how the car is seeing all of these lanes and also graphing out the possible trajectories that it could take through that scene. So that's a really, really cool little shot that he just showed relatively quickly. And then we finally get to something new that wasn't covered in AI Day 2022, which is motion planning using neural networks. That is something that has been discussed before, and that's part of that end-to-end thing that Elon Musk has talked about, version 12 of the software, having neural networks from the photons that come into the cameras all the way to the final output of the brake and the accelerator and the wheel turning and all of that kind of stuff. And more interestingly with Optimus, because it has, I think, 200 degrees of freedom. There's some amazing amount of degrees of freedom that Optimus has. And, clearly the car doesn't have that many degrees of freedom. So this is really important, especially for something like Optimus, but it's also going to make the car drive more smoothly because it's able to drive in a more probabilistic manner. Instead of having to make hard decisions, it can make probabilistic decisions, and therefore, again, should drive more smoothly and more naturally according to us human beings. And then we get to this really cool fleet auto labeling hybrid nerf system thing here. So I'm going to play some of the video, but you can see in this still frame capture that what we have is many, many cars driving this same intersection, the same area, over and over and over again, day, night, sunny, rainy, whatever that kind of conditions are. And what that does is it allows the Tesla team to align all of those different trips and utilize that to create a very, very tightly defined radiance field. In other words, a 3D reconstruction of what's going on here. And by doing that, they can actually create a ground truth of that scene without ever having to go there and take pictures of it or 3D LiDAR scans. And they can utilize that to do auto labeling and all sorts of other cool things. So very, very cool.
Multiple Tesla vehicles driving through the location, upload their video clips and other vehicle kinematic data to us. We bring everything together and reconstruct the entire 3D scene. So the polylines that you look, there is a cyan colored one. There's also a few other colored ones. Those are all different cars doing different trips through the world, and it's actually all very well aligned. Let me see if I can play it again. Yeah. The pink line and the cyan line that you see there, those are like different trips of different cars driving around, and everything is just aligned very nicely. And this multi-trip reconstruction has enabled us to, get all the lanes, road lines, everything directly from the fleet in the millions, anywhere on Earth, essentially. Once you have this like base structure of trajectories, calibration from all these cameras, you can really do a lot of cool things to reconstruct the entire scene.
So just going to pause here real quick. This is basically a hybridized NERF system, neural radiance field system, and it's projected out from all of the car's cameras to create a 3D scene that's very, very accurate and has all the detail you need to be able to drive in. And again, imagine this in the Optimus situation as well. This is not just for driving. This will also be used in Optimus in any conditions that Optimus finds itself in.
I'm not sure if the video plays quite nicely, but in my own screen, it looks very smooth, where you can see the ground surface. It's reconstructed quite nicely. There's like no artifacts such as double vision or blurring. Things are like crisp, look like geometric, they are correct. This is a hybrid approach to NERF and general 3D reconstruction. Sometimes in NERF, even though the re-rendered visuals might look very nice, the underlying geometry might be very fuzzy and cloudy. So we have a hybrid approach, which works quite nicely. You can see here, the barriers, the vehicles, even trucks, etc., are reconstructed pretty accurately.
So just really quickly again here, what we've got is a very, very detailed three-dimensional reconstruction from only 2D images. And the way that they do that is driving not one car through the scene, but many, many, many cars. And by doing that, they can align all of the effective virtual rays that they're shooting out in this neural radiance field. And they can get everything from being very fuzzy, which would happen if there was only one vehicle passing through, to being very, very detailed and, aligned with each other. And all of these things are probably down to less than centimeter accuracy here. And that is super important because, of course, as you're driving through a scene, you want to be sure that you're not hitting anything. And so you need to make sure that everything is where you think it is in that scene. And you can utilize this now, this as a ground truth, because once you've got things down to that accuracy, you can then say that like this little guy over here is a car, this is a tree, that's a building, I think there's some streetlights over here, curbs, streets, lanes, all of that kind of stuff is reconstructed in the scene. And you can take that and you can auto label it and then use it to train the system, especially on scenes where it might be having problems. You can run that virtual simulation over and over and over again with that scene without a human being really ever having to get into the loop of all this stuff. So it's pretty impressive how they can scale up their capability to do labeling through this type of technique. And this was a cool little extra that I had not found out about before, but basically the predictions that full self-driving can make allow them to ship, and they have shipped automatic emergency braking for crossing objects. So this is just a still frame, but you can see this red car here is pulling out directly in front of the person's car. This person was manually driving. Just before this, you saw them blow through a stop sign. They just went right through it. This red car was coming out and the AEB system kicked in and stopped the car before it would hit this red car, which is huge. That's an accident that didn't happen. That's people's days that weren't ruined and potentially people being injured and stuff, because of course, hitting somebody like a T-bone kind of thing like that is incredibly dangerous. That's a very, very bad accident if that happens. So this is an amazing thing, and you don't have to pay for full self-driving. If you just have a Tesla, it does this. And other car manufacturers just can't have something like this, as Ashok points out, because all of this crossing traffic, you have to do so many predictions and you have to know so much about the world that in order to just do what looks like a simple task requires all the stuff that they've done for full self-driving. So if you own a Tesla, even if you haven't, sprung for the full self-driving beta, you are still getting some huge benefits out of it, including something like this. And then we get to the really interesting part of this presentation. This is something new. This is something I spent a while talking with James Dalma about on the phone yesterday. He helped me to kind of crystallize a lot of the importance of what's going on here. But basically, all of the stuff that we just saw that they were talking about, and Ashok doesn't really say this here, but that's all stepping stones to what's coming up next. And I'm going to talk through a little bit of this today, but then I'm going to put off more of the discussion until Phil's talk, which, like I said, I'm going to do probably 2 days from now. So make sure you subscribe and all of that good stuff. But anyway, I'm going to talk a little bit about it today, but go into more of the ramifications of it with the next one because it fits with his video a little bit better. But anyway, so learning a general world model, what does that mean? That means that the neural network is able to take priors or the past and predict future outcomes. It sounds like exactly what we've been talking about already, but it's the generality of it and the fact that the network is able to learn without ontology. In other words, it doesn't have to be given explicit meaning. In other words, you don't have to label your scene. And if that sounds like a really simple concept, it actually is. And in a simple virtual world, you can create computational systems that will create these world models, and you can have characters like agents in those virtual worlds move through them and do really interesting things. The game of hide and seek that I think it was DeepMind did a few years back. I hope I've got that right. Who did that? But the little guys that were running around and they did all of those kinds of things. They can create a world model of what it is they're doing with a sparse reward system that they have. And you can do that in a world like that because it's not that complicated. The problem is in the real world, this gets computationally intractable very, very quickly because there's just a huge number of possibilities, a huge number of edge cases and corner cases and things that you've never thought of before. All of that stuff makes it very, very difficult. And everybody has basically just thrown up their hands and said this is impossible. So the really, really cool thing here is that we're seeing Tesla saying, we think we can do this. So now I'm going to play about a 3-minute clip where Ashok goes into detail about this.
We think there can be more to it. These tasks, like in the occupancy, for example, while it's quite general, some things are harder to represent even in that space. I'll probably go into more details shortly. So that's why we are working on learning a more general world model that can really just represent arbitrary things. So in this case, what we do is we have a neural network that can be conditioned on the past or other things to predict the future. And obviously, everyone has wanted to work on this forever. And I think with the recent rise in generative models like transformers, diffusion, etc., we finally have a shot at it. So what you're seeing here is purely generated video sequences given the past.
Okay, so I want to stop there. That's like a really, really important part here. Generated sequences. So these sequences that you're watching right now, and again, sorry that the quality is really, really poor here, but these roads and these lights and these trees and these cars around it, none of that stuff is real. This is just the dream, the hallucination of the FSD beta system. And that's the beauty of this world model. You can basically give it what's happened before. So you can give it a real world scene and you can say, here's your car driving through it. And then you just take away the future of it. And you say, now what's going to happen? And it will fill this stuff in and continue to generate this. Now, I'm sure a lot of people have seen this with, recent advances in like video, AI generated video and stuff, where it's able to infill things. Actually, you can do it for still frames too. But in video, you can see it infilling, and over time it gets worse and worse and worse, right? It starts to stray off of the reality. But at least for a few seconds here, the vehicle is able to predict what the future is going to look like from the past.
Videos, the network predicts some sample from the future, hopefully the most likely sample. And you can see that it is being predicted not just for one camera, but it predicts all the 8 cameras around the car jointly. And you can see how the car colors are consistent across the cameras. The motion of objects is consistent in 3D, even though we have not explicitly asked it to do anything in 3D or not even baked in any 3D priors.
Okay, so that's important too. They haven't told this thing the world is 3-dimensional. It's learned that. So that's a really, really crucial thing, right? You can imagine it like a baby or something, right? The baby doesn't pop out and just know it's a 3-dimensional world. The baby, he or she or whoever, has to learn that it's a 3D world. It's that kind of a thing where you have to actually have the experience to build a world model as a human being. That's what the computer is doing right now too. So it's not a trivial thing that they haven't told this is a 3-dimensional world, and that it has to figure that out on its own. That is actually crucial information here.
The network understanding depth and motion on its own without us informing it of so. And since this is all just predicting future, RGB values, the ontology is quite general. You can throw any video clip from driving or from YouTube or from your own phone. Anything can be used to train this general dynamics model of the world.
Okay, so that's a really interesting little point there. Is Tesla eventually going to create a generate your own thing where you can take a YouTube clip or take some stuff that you've filmed in your camera and actually generate more in a scene? That would actually be a very cool little product if they make it. So we will see what happens with that. But that was a really interesting aside that he made. And I thought it was worth, like, just calling that out and mentioning the fact that we might eventually have an app that will allow us to auto generate some stuff based on video or something that we already have.
Additionally, it can also be action conditioned. We can show a few examples. So here on the left side, the car is driving in the lane, and we're asking it to, okay, just keep in this lane and keep driving. And then, like I said earlier, the car is able to, or the model is able to predict all of the geometry flow by very nicely and understands 3D. On the right here, we're asking it to change lanes to the right side. Maybe we'll go back and play it again. So on the left, it's just going straight. And we ask it to go straight, the model goes straight. And then on the right side, we ask it to make a lane change, and it makes a lane change. And the past context is the same for both of these outputs. So given the same past, and when we ask it for different futures, the model is able to produce or like imagine different futures.
So again, this is really, really interesting. You can see the car actually generating the images of the car moving over. I'm sure IMU information and things like that can be generated as well. Semantics can be generated. So it generates whatever it needs to do to make itself go to the right or stay straight or something. And really interestingly, they say that what they can do is say go straight or take a right or something, which makes me wonder whether they've got a clip model or something embedded in this where they're actually able to associate what's going on with text. That would be really, really interesting if they're doing that. Not something that anybody's talked about, but it is something that they're probably going to have to do, at least with Optimus, if not with the car, for it to interact with human beings, because we like to talk to things. So clip is just, don't worry about the details of it, but basically it allows you to go from text to images, text to other things. It's a kind of an integration of text with other modalities. And so what I'm imagining here is that they're actually putting in a text input, which is continue driving straight or something like that, which means it has to be able to interpret that text and then utilize that to drive through the scene. So if that is indeed what they're doing and they're using clip or something like it to do that, that is super, super cool.
This is super powerful because, now you have essentially a neural network simulator that can simulate different futures based on different actions. And unlike a traditional game simulator, this is way more powerful because it can, represent things that are very hard to describe in an explicit system.
Okay, so again, sorry for breaking this all up, but explicitly describe, if you think about how you would describe a scene like this, and again, sorry, the resolution's bad, but just imagine a regular scene. It's not just like there's a car there, there's a road there. How do you describe that in detail that a regular computer would understand? What he's saying here is that the vehicle, this system is able to learn on its own without having to be given labels, without having to be told all of these things a priori. It's able to figure it out.
I'll show a few more examples, but then it is super powerful, and also the motion, the intention, and then the natural behavior of other objects such as vehicles is very hard to represent explicitly, but in this world it's very easy to represent.
So the import here is that you don't have to describe a scene anymore for this thing to learn about it. That's really, really important. And as Ashok says a little bit later in that video clip, he is personally amazed at how well this works. So even he is sort of blown away that this is working as well as it is. And so you might ask, why would we need this world model, which is very complicated and computationally super intensive and might or might not work, as opposed to just using the occupancy network that now at like a year old is like, oh, it works great, no problem. Well, there are circumstances where the occupancy network is not going to work. So I'm going to play a short clip and we can see some of those circumstances in these videos here.
Yeah, here's some examples where I think, something like this is going to be needed to represent like what's happening in the scene. Like there's a lot of smoke coming in one of the...
So right here, he calls out smoke. So if you look at this particular frame right here, suddenly you're in smoke. And imagine an occupancy network that all it's doing is saying, is this little voxel of space occupied or not? Well, when you have smoke, is it occupied or is it not? Because it looks opaque, which means it looks like it's something that you probably shouldn't drive through. But we as human beings are like, oh, that's smoke. I could see it coming off the truck in the other lane. And therefore it's something I should be cautious about, but I can continue driving. That's where an occupancy network is going to have significant problems. And that's where a world model that doesn't have to be explicitly told everything, but learns everything is going to have a huge advantage.
Pictures, like there's paper flying everywhere, that's going to be tough for, even occupancy, where, okay, you have paper flying everywhere. There's occupancy flow, but then how do you know it's paper? What do you know the material properties of it? There's like smoke. Obviously, you can drive through it, but it is occupying space and light does not transmit through. There's a lot of nuances to driving, and we have to really solve all of these problems to build a general driving stack that can drive anywhere in the world and be human-like, might be fast, efficient, at all speeds, yet very safe. And I think we're working on the right recipe for building this.
So that last little bit that he said is really intriguing. He thinks that they're on the right track, the right recipe for doing this. And that might be some of the optimism that Elon Musk has talked about recently about version 12 being good enough that it's not beta anymore. And of course, that was the last video that I did. That's why I said it was an hors d'oeuvre to this video here. But anyway, I think that that's really, really crucially important, is that they may be further along with this than they're letting on, because of course they can't talk about a lot of their research, but that they may have kind of tracked in or be focused in on something that they think has a really good possibility of working. And if that's the case, that is incredibly good news. But of course, the downside of all this is it needs an insane amount of compute power. And you can see this graph, which Tesla AI published around the same time that he did this talk. You can see that currently we're at, right about now, start of Dojo production right here. Their estimation over the next 18 months or so is this ridiculous ramp to massive 100 exaflops compute power. And what that means is, remember, I was talking about how intractable this problem is of doing a world model for a very complicated real world. What do you need for that? You need insane amounts of compute power. What are they looking at here? That's the graph, insane amounts of compute power. And then, of course, very importantly, this is built generally, not just for the car robot, but also for TeslaBot and all other friendly robots. I don't know what that means, but it sounds like they may have other options in mind. But the generality of this is going to be absolutely huge. So what are we talking about here? We're talking about one world model to rule them all. We're talking about something general where they can leverage what they're working on right now for basically any computer human robot human interface in the world. And then we get to the question and answer area, and I'll leave a lot of that to you to go watch. It's very, very interesting and very geeky as well. But a couple of them I wanted to call out. Number one was about voxel size, and the person asking the question asked, what is the voxel size that's being utilized in this? And this is Ashok's answer.
Yeah, again, these are like hyperparameters. Anyone can try with different voxel sizes. It's really a trade-off between memory and compute and what you're willing to do. So that these are not set in stone. It's not whatever the application needs. Even between the robot and the car, you can configure different sizes, and they have different needs. So it is really configurable, and optionally can be made queryable, as in you can get arbitrary position by just having the network emit small MLPs or something like that, where you can query to arbitrary position. Again, it just comes at compute. So it's up to the design of the downstream tasks to determine, what is the base size, you need these MLPs or not, and you get away with some simpler formulations. It's really up to, there's large design space here.
So basically you can pre-configure something. So like with Optimus, you can make the voxel size smaller because it's moving slowly through a world that's much more detailed, like inside of an office building or something. But there is the option of dynamically changing the voxel size as well. I'll go into that more with Phil's talk because he goes into more detail about that as well. So the next person asks, what is the state of the world model? And the really interesting thing is to look at Ashok not answering the question at first and thinking about, what am I allowed to say? It's a really interesting pause here, a dramatic pause.
Only thing I can say is that it hasn't shipped to customers yet, and we are still optimizing it. Maybe later this year. I don't know.
So really interesting, because he said later this year after a very long pause where he thought about what am I allowed to say. But that indicates to me, even though they're kind of playing it close to the vest and going oh, we haven't really figured it out yet, we don't know what we're doing, it sounds to me like they're further along with this than they're letting on if he thinks that later this year we consumers are going to get access to that. That is really impressive and something to look forward to in the latter half of 2023 or maybe the first half of 2024 if he's being a bit optimistic. Elon, of course, has an optimism bias quite a bit, but Ashok tends to be a little bit more, on the nose about things. So if he's saying the end of 2023, early 2024, That sounds pretty good to me. It sounds like we might actually get a hold of something like that by then. So that is super, super cool. All right, so that's what I've got for you for this CVPR presentation. Like I said, it's very, very geeky. There's a lot of stuff. Hopefully I explained some of it reasonably well. A lot of it was rehashing things. So if you've watched other of my videos, you'll have a good sense of this already. But the world, building the general foundational world model here is something very, very new. And I'll go into more detail about that with the talk that Phil does. All right, I hope you enjoyed this video and found it fun and interesting and thought-provoking. If you did, please do like it so other people can find it, because that's how YouTube's algorithm works. And of course, consider subscribing for more of this kind of content. As always, a huge shout out to my Patreon patrons, my YouTube channel members, and also my Twitter subscribers. Thank you all so much for supporting the channel in any way that you can. And of course, if you want to join any of the teams, just check out the links in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have TeslaBot t-shirts, the Tesla meme t-shirt, Success is a Possible Outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on and on. So check it out. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a car, a solar roof, a Powerwall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.